Hello there, my name is DOH-NANI from the Department of Statistics and Actuarial Science, KUNIVERSITY, Kumasi, Ghana. As I started earlier with a video, differentiation and integration, it's just a continuation of what I started, or the video I just uploaded earlier. Before we continue, I would want you to kindly subscribe to this channel, click on the notification bell below, share, like the video, and then as well as comment on it, and let me see your ideas on these videos. Yes, so I started with the differentiation and integration in couples, and we are still on differentiation. There are some rules in differentiation, and I just want us to tackle them. Now, we're going to talk about the chain rule, the quotient rule, and as well as the product rule. Now, there are some special functions, and henceforth, we need these rules to aid us in finding the derivative of those special functions of special expression. Now, with the chain rule, I just want us to consider this third example, the third expression, to find out how we are going to actually, find the derivative of that function using the chain rule. So, now we are going to represent V to be equal to mx1/3 plus nx1/2. Then if that is the case, now our expression is now going to be y is equal to v exponent 1/3, that is the cube root of v. Now our dv is equal to 1/3 v, that is 1/3 minus 1, giving us the expression 1/3 v exponent negative 2/3. Now, we are now going to find the derivative of v with respect to x. So now, dx is going to give me 1/3 m x exponent negative 2/3, then plus n/2 x exponent negative 1/2. Now finally, our dx is equal to dv dx multiplied by dy dv. That is dy dx is equal to, now our dv dx is this one. So we put it in the bracket 1/3, or in a better way, m x exponent minus 2/3 all over 3 plus n x negative 1/2 all over 2. All this in an expression multiplying dy dv, and this is dy dv, which is 1/3 v exponent minus 2/3. 1/3. Now we know our v to be what? Mx 1/3 plus nx 1/2. So multiplying the whole expression of mx 1/3 plus nx 1/2 all exponent negative 2/3. Exponent negative 2/3. And this is the derivative of this function. Quite complex, but when you take your time in solving it, you will get it clear. So we are going to try solving this expression. This another complex expression or complex function of which we need to find the derivative. And henceforth, we are going to use the product rule. Why? Because we can see this function, a whole expression, multiplying another expression. and henceforth we are going to appropriately to find the derivative of this kind of function. You have to use the product rule. And in this case, we are going to name this expression v. Our v is equal to the whole of this, that is x squared plus t x cubed, all exponent 1 on 2. Yes. Then we are going to represent this one by k. In fact, I would want to use this one by m. Then I'll use this by m. You choose appropriately. Now I'm having some I used some variables for my coefficients. So in this case, I have to use a different variable in order not to make us confused with them. So using I'm representing m to what? Ux squared plus vx. And now with the product rule, to find for dy dx, we are going to use v, and in this case I'm representing m. So m du, so my dy dx is equal to m dn dx. Then plus n dm dx. So in that case, now my dm on dx implies and what can we see over here? There is another expression that we can form from this one. We can use the chain rule to solve this function. Quite complex, but you have to be so be so skilled so that you will be able to. So I can use k. So in that case, I'm going to get dk dx multiplying by dm dk. And in this case, if I'm representing this whole expression by k, then my dk dx is going to be 2s plus 2sx, then plus 3t x squared. That will be the expression for dk dx. Then dm dk, so this whole dm with respect to k will be equal to 1 on 2k, 1 over negative 1 over 2. That will be the k exponent 1 over 2. So I'm finding that dm dk, and here is dk dx. So finally, I'm going to multiply this by this. So I'm going to get the expression 2sx plus 3tx squared. That is dk dx multiplied by dm dk. And with dm dk, it is 1 on 2. And the k is what? K is the whole of this expression. So I'm multiplying the space, so I'm just going to put it over here. So sx squared plus tx cubed, all exponent 1 on, so this is my k. So I'll divide here by what? 2. Then exponent negative 1 on 2. So here, exponent negative 1 on 2. So this whole expression is multiplying this. And that will be for our dm dx. Yeah, so I have written the expression over there in a nice form so that we would appreciate the solution for dm dx. And this is in variables, and so it's kind of quite complex, and we are not really getting it. But when I start with it, I'll give some examples with figures, and in this case, these expression S, T, and other stuff will be leaving us so that you have the feel of the, a good expressions or a good calculations over there. So we are now done with our dn dx. So it's kind of complex. So we are going to tackle the dn dx. The dn dx. So it's going to be dn dx is also be equal to 2ux plus what? V. 2ux plus v. We are just finding the derivative of this one. So 2 multiplied by this. So 2 plus v. And that will be that. Now we are going to find our dy dx. So our dy dx. Our dy dx is simply this one multiplied by m, and this is our m. So I just want to have a nice piece for it. Now, our dy dx is simply going to be, our m is sx squared plus tx cubed, all 1 on 2. Then multiplied by the dn dx, and our dn dx was given to us by what? 2ux plus what? V. Then plus our n was giving us ux squared plus vx multiplied by dm dx, and our dm dx is simply 2x plus 3tx squared multiplied by sx squared plus tx cubed, 1 on 2, negative 1 on 2, all divided by 2. So this expression is multiplying this, then there's this. So you can actually, rewrite them and then do some cancellation to get a minor expression. That is how complex some expressions can be in differentiation. That is why we need these rules to help us or to assist us to do the derivatives for those complex or special expressions. Now, we are going to tackle this expression. Now we're going to consider the quotient rule in solving such an expression that has to do with fractions. We need the quotient rule to aid us or to assist us in finding the derivative of such expression. Henceforth, in this equation, we are going to represent this one by what? Our u, and this one by our v. So I'm going to find the numerator. The function or the expression as the numerator is going to be represented by the u, and that of the denominator is going to be represented by the v. And in that case, I'm going to use the quotient rule. That says dy dx is equal to v on the u dx minus u on the v dx over v squared. And if that is the case, then I'm going to write my v squared to be cx cubed plus dx plus e all squared, and this is my v, so v squared, this is v squared.